Good morning, everybody. Welcome to the Prototype 1 training session. This session will be devoted to the work package number 4, and this will be the first session of this prototype. Okay, and this is the agenda. First, we are going to review dependability assurance case modeling with Alejandra by Tecnalia. Then we'll move to contract-based multi-concern assurance by MDH by Irfan Silvio. Then the last point will be system dependability co-analysis, and there will be several presenters by CEA, A4T, and MDH. Okay. Every time you have questions, please take down notes, and at the end of each part, at the end of each slot, we will ask for questions, so that will be the time to answer all of them. Okay? So we are moving the presenting rights for the first speaker, which is Alejandra. Change floor to presenter. And now I am okay. You and me just okay, perfect.
So good morning, everyone. Thanks for coming. So the idea of this session is to talk about the dependability assurance case modeling. I'm assuming that you have some experience creating assurance cases, or at least safety cases. I'm also assuming that you know how GSN works. I will do a brief explanation at the very beginning. If you don't know, I really recommend reading this document by the GSN community, which explains in depth how to use it. And the other thing is, I'm assuming that you work on assurance cases on the different case studies on the project. All this functionality it's included in the assurance case editor. Okay, so if you don't know where to find it, just go to the assurance case editor. Somewhere you will find it, all this functionality I'm explaining. I will show it at the same time. What we will do, we do create, edit, and manage documentation in a modular way, doing this composition, and how to make this dependability argument. The first thing, just to remember, I would just start remembering some of the concepts. The safety case, when we talk about safety case, and it appears in hundreds of places in literature, it's about a safety justification plus all the supporting material. So you have some, it's a way to encapsulate all the information about safety. When we talk about assurance case, which doesn't appear so much in literature, but it's nearly the same thing. The main difference is that we are not dealing only with safety, we are dealing also with other concerns, like security, like compliance, like availability, reliability, all this. So as we are working in Work Package 4, which is about the multi-concern assurance, we're always talking about assurance cases, because we are not talking just about safety, we are also talking about security. We could talk about other elements, but mainly we'll be talking about safety and security. If you remember how we work with the AMASS platform, just remember that we have a concept of the assurance project, where we have our assurance assets, and we deal with argumentation, evidence, process, system. Well, here I'm talking about argumentation, okay? If we go on the tooling, whenever we go and create an assurance case, we have like a list of folders. We will use this folder, argumentation folder. For every assurance project we use the folder. So now we know where we are. So why are we doing these assurance cases? Well, one of the things is that we are able to show arguments that our system is safe or secure in a given context. Always the assurance case is not true for everything, okay? We need to have some operational or an environment and a scenario where it's true. And it's usually done because we need to make some formal assessment. Usually it's because we are asked by the certification authorities to make one of these, or we are releasing our system to a service and we want to put all this information there. That's the primary thing. Mainly, we are doing it because we are asked to. But the other thing is, it's really a good thing, the secondary purpose, because it helps to reduce the risk. Because we have to show, from the safety point of view, we have to show that our hazard and have been identified, have been mitigated, the safety analysis are complete and have been doing in deep detail. If we look at for security, we're also going to show that we have identified the threat. We make this vulnerability analysis. We know that we are covering our threats. And from the project point of view, we are showing that we are fulfilling the safety requirements, and we have a strategy to fulfill it from the very beginning of the process. So if there is a problem, we identify it earlier, and we go and attack it and put all of our resources to solve it. It is important. Never do the assurance case at the end of the development. Always do it from the very beginning at the same time as you are doing the development. That's the best practice. So the main elements that we have are on one hand, this is a nice drawing that we have from the ISO 26262. So we have some safety evidences. This is the results because we are observing, analyzing, testing, simulating, estimating the properties of our system. And it could provide information about how is the system. But just the evidences does not provide what we need. We also need arguments. We need arguments because it's an explanation of how the available evidences can be interpreted, can be understood, indicating that we are acceptably safe, secure. And usually it's because we are complying with requirements, because the hazards are being sufficiently mitigated or avoidance. We have mitigation of threats, all this. We need both, because imagine I argue, well, the earth is flat. That's my argument. But which evidences do I have about that? If I do not have evidences, then I can say that my argument is unfounded. It's not okay. It's not a good argument. If I come and say, well, I make a test, the result is 7. I say, 7 of what? If we do not have an explanation why we are doing that test, what is the objective of making it, what is really going to be providing me, then I can say that my assurance case is unexplained. So I need a combination on both. I really like this picture because if you're coming from the computing world, or you have a very logical head, this is a good way to understand what are we doing here. Because I'm talking about arguments. Well, okay, but show me how it works. And it's really looking in a logical way. So if I have an evidence, like evidence 1, if I have this evidence, I can really support that claim 1 is true. If I do not have evidence 1, claim 1, I don't know if it's true or not. If I have evidence 2, I can say claim 2.1 is true. And if I have evidence 2 and 3, I can say that claim 2.1 and 2.2 are true. If these both are true, then this is true. If this and this are true, then this is true. If one of them is not true, this is not true. So it's pretty logic. Think of a Boolean logic. It's very easy. Just think that a claim can be true or false. It's only true if I have a supporting evidence. I can't decompose my claim. So I do not have a specific evidence to say this is true, but I know that if I say this and these are true, then I get it. Well, I said that you should have some GSM knowledge. This is the basic elements that you have in GSM. This is the main basic. Well, we have the goals. Okay. We have to show that the goals are broken into sub-goals. Okay? And at some point, these goals should be supported by evidences, this solution, these circles. For doing that, we have to make clear strategies, all these parallel ones. So we have to show which strategies have been adopted for doing this. And sometimes we do need some rationale for the approach. For doing that, we have assumptions that we make and justifications. And we have to show the context in which these goals are stated. That's why we have this. To connect all these drawings, we have 2 arrows. This, you see, it's right in the middle, it's open, it's in the context of. This, complete black, complete field, it's solved by. This is the main basic. And we can work in 2 ways. We can work top-down or we can work bottom-up. Top-down, well, we have some conclusions, some top goals that we have to show that, well, we have sufficient evidence that support it. But sometimes we do not have a clear way of these conclusions, but we do know which is the available evidences that we have. And from that evidence, we can extract some conclusions. So we go bottom-up. If we go top-down, this is a nice method. It's called the 6-step method. It was made by the GSM community. So remember at the very beginning I told you, well, there is a nice document if you don't know about GSM. This is a document from the GSM community. Well, there it explains this method. So if you haven't made assurance cases for a while, it's nice to make it to read it again and remember some of the ideas it has there. So now we say, well, we have to argue about dependability. Well, how do we argue about safety, for example? We have to show that our risks are controlled. How we do this? Because we say, well, we have made a nice hazard analysis. We have to say how thorough was that analysis, have we identified all the hazards, are the assumptions that we have made credible, all these hazards that we say that we are mitigated, can we say that they are really reduced as low as reasonably possible? Sometimes we also have to look, well, are there other design strategies that have been overlooked? This is very interesting because when we deal with safety and security, sometimes the different strategies affect different. We will talk about this later. I can say that, well, if we deal with safety, the safety case, the assurance case for safety, it's much more than the hazard log or just a list of safety analysis. We have to make it all interesting, all coherent and consistent. So we look about safety. Well, this is a typical argument, typical evidences. For security, it's more or less the same. We have to show that we make a threat analysis, that we have identified all the threats. We make some vulnerability analysis. We can say that we have covered all the vulnerabilities. We are go there. So on the assurance case, we usually will have all these evidences at some point. And in AMASS, we will go for everything. So we should support everything. This is an example of a fragment. So we say that our system is dependable because it's meeting its dependability requirements. Just remember, this is done in a context where all these dependability requirements are specified in this document. So we can't link this to a specific document. How are we going to argue about this dependability? Well, we have here our strategy. Well, we will argue with arguing about the different dependability attributes. So we have reliability, we have availability, we have security, each of them. So for the dependability, we will need to deal with all these three. This is a new element. If you see this diamond, it's under development. I haven't finished. I will go on here. So how does this work? We go here to write an assurance case. Go File, New, and we can say arc diagram to repository. That means that we will save our assurance case in the common repository. We can work both in files or in the repository. I will go here because I have some examples. Yeah, this is some kind of an example. And this one is another one. No. You can see the different elements that we have here. Here we have all the elements in GSM. And here for modular, which are the things that I'm going to talk about it now. This was part of prototype core, so it keeps going on working the same. But now we have to go for modular arguments and how we deal with composability. Well, we say that modular assurance is the idea of divide and conquer, because we have to talk about so many elements, so many concepts that are so hard to talk. But this idea of divide is not that easy. It's not that easy because safety, both safety and security, both of them are a system property. So it's hard to say, well, I go up to here. This is my boundary. This is your boundary. It's not so easy. But that's why we're here. Why we do this? Well, also we go for modular arguments because these assurance cases, it's very strange that just one person may call the assurance case. Usually we have different people, different teams, or even different organizations, including one. So imagine we have a system like a vehicle. How many subsystems does it have? So maybe we are asking the assurance case for one of the components to a supplier. And when we have the complete vehicle assurance case, we need to manage, we need to deal with all the assurance cases provided by all the suppliers. So how we deal with this complexity? It's so hard to think of all the subsystems that are in one of our products. So we decompose it into subsystems. So just for an example, in avionics, we have to make one safety case for the airworthiness of the plane. And also, well, we have several safety cases for the separate systems, like navigation, engine control, flight control. And then we have to integrate all of them. The idea comes from this software architecture. So the software architecture, we say that we can structure is the structure or structures of a system which comprise software components and the externally visible properties of those components and the relationship among them. So we can say that the assurance case architecture is very similar. We have a high-level organization of the assurance cases into components of arguments and evidence, the external visible properties of these components, and the interdependencies that can exist between them. So, yeah, more or less think of an assurance case architecture, the same as you are thinking of a software architecture. So, what is visible? We can say that there are public claims, calls addressed by those modules. The evidences provided in the module are visible. The context, for example, the assumptions that we make, that are also important. But we have to consider interdependencies. So we have claims that need support, and they do not have a supporting evidence within that component, but in another one. So we have here, we can have claims addressed elsewhere, evidence is presented somewhere, context defined other ways. All these are these interdependencies. But actually, they are useful when we have objectives and arguments that complete each other. We have the collective evidences of and the assuming context as consistent. So then it's useful. And the other thing is when we connect and we compose two argument modules, how do we explicitly show that connection? That connection is done by argument contract. And why we are going with this? Well, feasibility in the development, time and space. It's easier, we can work in parts of the system in parallel and also in space. Imagine you have to make the diagram of the assurance case of a plane. It's going to be huge. It's difficult to see it. If we go in pieces, it's more easy. And we can isolate changes. That's why the contracts are so important. So how do we go with these extensions? Well, we say that we are going to show some elements that are externally visible. So the claims that have this symbol, we can say that they are public. They can be requested by other modules. This is a claim, or this one. Both are what we call away goals. So it is a goal, it is a claim that I do not have the supporting evidences within this module, but in this other module, there it is, and there is well done explained. Sometimes we go and say, well, let's go and see a module view. It's a way to show this from high level the architecture. We can show the high level view of how we organize all of our elements and the relationship. So when we start saying, well, let's create our architecture, the architecture of our arguments, we can go and say, well, this is a module, this is an argument module. Inside here, I will have all my claims. And from here, I will decompose it into function A, function B. And all these should be in the context of all this. We make a module view related to different multi-concerns. This is something that we have made within Work Package for work, where we say, well, we will go and deal with the system multi-concern assurance. How we will deal with that? We will decompose it into system goals allocation. For all these, we will have at least one module per each of the concerns that we will deal with. This system goal allocation will be decomposed into system requirements, and in the end to components. And all these requirements, we can decompose it into the different concerns. All these, at the same time, be in the context of what we say the trade-off between the different concerns. I don't know if you remember, I will show you later. The other thing I talked before, it's about the argument contract. This is an example of an argument contract. This was proposed by the Industrial Avionics Working Group. They make a nice paper. At the beginning, they say, well, why not make this argument contract? Just make some tables. And then when they work on it, they say, no, why not actually use DSN to explain how we are connecting the different modules. And this is, in the end, an argument contract is a piece of arguments, explaining how we are connecting one goal to other. So this goal, imagine, is in module A. Okay, at the very end, we will connect it with the module B. So the goal in module A here, with all the context included in the module A, how can I support it? I will support it, arguments about all the goals that provide support to this. In this case, I will provide it with this goal in module B, and with all the context inherited in module B. Okay, this is just a generic contract. Could be done differently, but this is like a nice, good practice. So how does this work? Next work. Yeah. So this is a module view of the of a system. We have different modules. So you see here we have the system goal specification, system requirements on all this. We can use elements from patterns. So when I specify my architecture, I would say, well, I will need, I don't know how many, but if my requirements are decomposed into n components, then I will need n of these. How to make all this? Well, for modules, for modular argumentation, I have in this section all the drawings. Okay, I just have to choose one and draw. Say one. This is module A1. Okay. Other important thing here is when I can double click on this area of the tab, and I can go to the inside. In this case, it was empty. But here, just by double click on this area, I can open and see what is inside. Okay? How I do that? Because in this location, I put the address of where it is. But how can I do this? Because it looks into the preferences. So I go Window, Preferences, and it is important that you have this configured. Okay. I have in files or in the common repository. Okay. In the common repository, there is a folder, high-level folder, which is called argument patterns and argument modules. If I do not explicitly say where I'm going to make the content of that module, I will create a new diagram and store it here. Okay? This is pretty nice because for reusing, I can later on go and get all of this. So please, important, make this configuration before you start working. Yeah. So this is usually the process that we go when we deal with how we do this assurance case. So first we define the assurance case architecture and create this model view. Then we allocate system goals to concerns, derive the system requirements, create our assurance case. That's all the time. Then sometimes we have to analyze this interplay. This is something interesting because this is what I'm going to talk about now. Well, this was an assurance case structure, which I will call it. When we have to show the interplay, we have identified that we need a few more drawings to explain. Sometimes what we do is we have a claim that is true, but it depends on the fulfillment of another one. So claim A will not be true if claim B is not fulfilled. That's why we usually do in the context of. So even though I support claim A, it will never be okay if I don't, if claim B is not true at the same time. So this is an arrow that we have it before, but this is a way to make it. This is another thing which is quite interesting, usually when we deal with concerns. So I can go and say, well, this is very safe, and I make it very safe, but it could conflict with another measure, actually. It could be very, very safe, but it's not secure. You put the password in plain text. Yeah, it is very safe. It doesn't matter. Everyone could read it. There are different ways to read it. Yes, that's one of the problems. It's not secure. So when we have this conflicting, then we have this arrow. The other one is the supporting relationship. So an assurance measure for attribute A is applicable to assurance attribute B, so that one assurance measure can be used to replace the other one. So we have two options to solve it, and we have different options, and it's a way to show the different strategies and design decisions. So we have different decisions. Usually, a claim is in here, and the claim is in here. Okay. And we say, well, in this case, will be 1 out of 2. We have two different, and only one needs to be true, and then this one is true. If it's 2 out of 3, then it's 2 of the mechanisms should be true to make this one. It could be, you could have more. Let's put that with examples, because I'm saying in a generic way, and with examples it's much clearer. So this is the dependency, the first one. We can say, well, the communication system between the vehicles should be available. But this claim would be true, depending that claim B, the communication of the system is designed to prevent deny of service attacks. So this is okay, but in the context that this is also okay. Sometimes, as I said, the conflicting relationships. For example, the position sensor data uses a 2 out of 3 architecture to ensure correctness of the data. Yes, this is very nice, and usually it's something that we use for safe. However, if we're thinking of security, while the attack surface has been reduced, no. The input from the sensor is a unique channel. No, that's not true. So if we're thinking from the security point of view, that would be a nice claim, but it's against a very usual safety solution. So to solve this, we have these conflicting relationships. I have to say, from the methodological point of view, that we can have these conflicting relationships while we do the development. But once we finish, and that the product is going to put into service, we mustn't have this kind of relationship. This should be solved. And the other one, the supporting relationship will be like, while the position of the predecessor vehicle shall be accurate. Well, not both claims could be true. Only if one is true, it's okay. So the position of the predecessor vehicle is calculated using diverse software with 0.001 deviation. Could be this true or could be this one. Position of the predecessor vehicle is calculated in hardware and in software with less than 0.002 deviation. So just with one of them to become true, it's okay. But we have different design decisions here. Here we have, well, use diverse software, and here we have, well, use diversity because you have software and hardware. You can choose one option. So yeah, let's make an example. Yeah. This is a huge argument. By the way, if you want to see it, it's on the repository on the, I think it's on here, yeah. So, case study 3, CACC, rear collision hazard. This was one we made for the project. And well, we look at the real collision hazard that has been has been adequately addressed by multiple concerns. We decompose it, and here we have different ways to see this dependability. So one, it was, yeah. So we have this element we're using contracts for this timing contract. Well, the CACC system implements the CACC system timing contract. This timing contract is connected with Work Package 3. It's a design contract, which is very nice. But if this is true, you see there is a conflicting thing. The cooperation awareness messages are encrypted. No. If we do this, the other one will not be true. So here it's a nice conflicting. How we use this? With this arrow. You choose it, and you can go from one claim to another one. Okay? Yeah. Let's see if I have another one. No. But so here you have quite a nice assurance case that you can have a look at it, and it's quite full with all these examples. Another thing interesting, well, remember we took in one of the deliverables for Work Package 4, we remember that there was this trade-off pattern. This was published by George Despotu and Tim Kelly in a nurse paper. And it was a way to make arguments about the trade-off. This is one of the patterns. This is a nice thing because I can talk again about the pattern. Okay. Well, we store assurance case. We have this pattern because we want to capture successful argument approaches that can be used in the assurance case. It's the best practice. We can encapsulate the company expertise, how certification approaches used before was okay, and tools for trade. Okay, the new capabilities. I would like to show it. Well, the main reasons that you can get problems using the patterns that we're using on the core prototype before is that you didn't configure the properties. So now we can store your argument pattern. You can store your argument patterns both in files. So I have here my argument patterns. How many? And I can store this on the repository. Which I don't know where they are. How I can do it? I go into Windows, Preferences, Open Third, Argumentation, and here I have my properties. If I do not have these properties, okay, then if I go to Templates View, I won't get everything there. So I have this is Pattern Explorer for files. So I will find my files here. My Module Explorer. So all my modules in files will be stored here. This is in the repository. The patterns are stored in the repository, and the patterns are stored in the module. Modules are stored in the repository. And what happens? Well, this is a case study. Let's create one new create this is to create an assurance case. I will go and say I will create it in testing, and yeah, I will call it training 1. Okay, in the same place. Okay, so how can I use the patterns or the modules? As I said, you can store them in files or in the repository. Actually, what you do is just drag and drop. You have there the pattern. What's the difference between the arguments and the pattern? Well, this is not the one. The argument pattern, you have here all the drawing. Okay, nice one. It's in there. Usually, sometimes you have to the things that are with patterns elements, you have to instantiate them. But when you go for modules, there is no need for instantiation. You're actually going to reuse completely. So you will go one, create, and what I do have here, it's a module. And if I double click on it, I will get, I should look for the other one. I think this, yeah, modular one. This one is, you can go and get the elements that are inside. Okay, just by double click. What has actually done? Well, in module A1, when I just do module and drag and drop, the content, it will be here. It will be stored there. So in the place where you store the modules, over there you will have the information. And you double click over there and get the content, whatever you have created before. It's ready to use. And you can just by double click browse and navigate through all this. And with this, I finished my explanation. This was everything and all the new things that we have in the prototype P1. If you have any question, now it's the time. No question? Do I make everything very clear? Then I could pass the presentation to the next presenter.
Yes, can you move to Irfan?
Yeah?
Thank you, Alejandra.
Thank you.
Okay, Irfan, we can see your screen.
Okay, can you hear me?
Yes, right now.
Great.
Yes.
Okay, this is something for later. I will first have a short presentation and then we'll go through a demo later. So I will talk about multi-concern assurance from the component contract side, which means from the system domain. Let's start with an example that I will then show concepts on later. So I've been using this wheel loaders, and as you may know, each wheel loader has a lifting arm. It can this arm which can go up and down and do some movements, and it consists. The controller of this arm consists of several smaller components. For example, one getting the position of the arm, one performing automatic positioning of the arm, where the operator can press a button and move the arm into predefined position, or the operator can manually move this arm, and so on. And some of these wheel loaders have support for remote control, which means that these inputs can also be generated remotely, not within the machine itself. So that's what makes it a nice example for considering multi-concern assurance, because we need to assure that the system is both fault-free, but also that it's secure enough that someone can't take over this whole thing. And this is just a sketch design, for example, one of these loaders, where you have this loading arm automatic positioning component, which is something that can be moved from one system to another, and it has an arm controller that's performing actually the command, and the hydraulics that's doing the whole lifting and so on. So what we have, some hazards that can pop up here. Unintended arm movement. It can happen if input controls are wrong. For example, if the angle sensor of the arm is wrong, then we can have unintended arm movement. Ground speed, for example, and so on. But we can also have a hazard like arm movement during high speed, which can be dangerous. So that's where, if we have wrong ground speed, then it can be a problem also. So it can happen. These can happen due to faults in the system, but they can also happen due to unauthorized positioning commands. So as I said, we deal with the component contract aspects, meaning we start from the system modeling side. So consider that we have this in this domain. So Alejandra mentioned the argumentation contracts. So this is something a bit different. Contract here for a component is a pair of assumptions and guarantees, such that the component guarantees its own behaviors if the environment of that component fulfills the assumptions. So if you take an example here of this loading arm controller unit, this top component would be the system that is composed of several smaller components that are interconnected in different ways. What we do with contracts here, we specify a contract on each hierarchy level for each of the components. And then we connect those sub-component contracts with top component contract, such that there is this relationship called refinement that established between those. And if we can show that the refinement between those holds, we can also say that that the subcomponents correctly implement the contract of the top level component, meaning they constitute a good enough system, so to say. What's the purpose here? Well, if we have some requirements allocated to this loading arm controller unit, like requirements about timing, requirements about some of the things that we mentioned before related to those hazards, then those requirements can be matched with the contracts such that we can show that if those contracts are satisfied, then those requirements that we have allocated to these components are also met by the system. So this deals with contract-based design side. So to support assurance based on this contract-based design, we associate in this AMASS prototype 1, we associate assurance assets with contracts. Meaning, it's not enough just to say, okay, the contract checking has been, or the contract refinement checking has been successful, hence the requirements are satisfied. We need to provide some more evidence. We need to provide evidence that actually the components behave according to these contracts, the actual implementations. So we need to have some trust in these contracts, that they're good enough. So that's why we associate certain assurance assets with those contracts. So that we can actually support assuring that the system has fulfilled certain requirements that address some hazards in the system. So good that Alejandra already introduced these patterns and GSM. So this would be something what we can argue about based on this contract-based design and assurance. So if we want to say that the requirement is satisfied with certain confidence, then we can do that by first assuring that the requirement correctly actually is correctly implemented by the corresponding contract. That is, if the contract itself does not really capture the essence of the requirement, then the fact that we have satisfied this contract or that we have proven that the contract is satisfied doesn't mean much for the requirement itself. So that's why we need to establish that this connection first is let's say, good enough. Then, once we have established that, then we have to actually show that this contract itself has been satisfied with sufficient confidence, meaning that the composition is correct. For example, that we have there with refinement and connecting to subcontracts, that the assumptions towards the environment are also met of this contract, and eventually some evidence that we might provide that can communicate confidence in this contract. For example, that can be if we have a contract saying something about timing of the component, we might perform some timing analysis or simulations and whatever not verification to show that actually this component actually complies with this contract, that in the particular environment it will execute within a particular time interval specified in the contract. So this is an example argument pattern that we can use to assure based on component contracts. And in AMASS P1, it's been shown in other work package training sessions. We can automatically instantiate these patterns from the information in the system model regarding the contracts and the attached assurance artifacts. So if we look at the safety assurance case structure, this would be a standard structure that you could have. Here, where we have system goals, for example, that reflect the hazards in case of safety case, then we would have different system requirements to meet these goals, and then those would be allocated to the components where each component itself needs to show that actually meets the particular requirements and so on. So this could be a structure that will simplify things, because if we make it a monolithic assurance case, then it would be huge. And it would be very difficult to also make, but also review. So modularizing it helps quite a bit. And especially if we talk about reuse, then we could then, if we're using component one, we could also reuse this module with that component. Anyway, so this would be a structure that can be focused around a single concern. For example, if we have a safety assurance case, then we could have this structure to talk about safety goals, safety requirements, and then the satisfaction of safety requirements by each component. But also it could be used to cover all concerns jointly. There we would have mixed system, for example, system goals regarding safety, security, and other concerns, and also requirements regarding all of those, and each of the components would then have to address each of the different concerns. So how would that actually look? So how to efficiently cover this from the to have these concerns assured independently? So we've been looking into the system modeling side and what we can do there, because if we're already automatically making this structure, then we could improve it with respect to different concerns on the system side. So the idea there was that we tag each component contract, with different concern attributes. That would mean that the different argumentation parts that are generated from those based on the contract-based assurance, the contract-based design, the different argument parts that we can see here, we can automatically identify if those are safety, security, or whatever concern related. And by connecting them, we can connect them to different requirements on the system domain, and then we can have different viewpoints of the assurance case itself. So, for example, then we can easily extrapolate a safety assurance case where we would have all the safety requirements and the argument patterns that are supported by those. But also we could have security case and argument fragments that are related to those. What is interesting here is that we can notice that there may be some contracts, some component contract, and hence their corresponding argument fragments that are supporting multiple concerns. So that's also an interesting thing to know when we want to explore the interplay between the different concerns. So how possible structure would look like, this is what Alejandra already showed. That would mean that for each of these on the that we said before, system level, system goals, system requirements, component assurance case, then we can divide those based on concerns, as said before. So such that each of these can have separate parts for concerns, and then the trade-offs, the interplay between them can be discussed in a separate module. So the generation from the chess system model to OpenCert assurance case, we implement that to have this in mind, such that we generate the small assurance cases for each component by considering these different concerns there, and also on the system requirements level. So we will go into the tool now to see how this works actually. So this is block definition diagram for this loading arm automatic positioning, loading arm controller unit. It has this system level with all the different ports, and we specify different contracts for the system level, and then we have a set of subcomponents for this. And this is internal block diagram that shows, okay, this is the system, and these are the several components that are interconnected. We have the arm positioning, which determines the position of the arm based on the sensors on the arm. This is the loading arm automatic positioning, which means this will be moving the arm automatically to a predefined position, and this would be arm controller that's actually issuing the command to the hardware. So we can take a look at the requirements. Let's see. Requirements on the loading arm component unit level that we have defined. This is just a few requirements. For example, we can have a requirement that's going to be talking about the stop position of the arm and its accuracy. Requirement on that loading arm positioning cannot start without user initiation, for example. So we talk here about we rather see the hazard on unintended arm movement. But also we can have requirements on security, for example, that only authenticated users should be permitted to control the loading arm, which means that any signal that we get from the operators needs to be authenticated. We need to check that. So we can have corresponding contracts on these things. For example, we can have a full propagation contract that's going to be talking about full propagation behavior of the loading arm, and if we want to guarantee that the command is not faulty, then these are some of the assumptions that need to be made to be able to guarantee this. So what we can do with respect to concerns here, we can, since these formal properties that we describe here, and they should be reflecting the requirements. What we can do, we can assign each of these with a different concern. Okay. And then we can, for the sake of assurance, we can immediately, since not everyone can read these formal specification, for example, LTL-based specification, to support assurance, what we can do here is describe in a context statement what this actually means. So, for example, here, if for the command, for the arm movement command to be accurate, at least one angle sensor should not be faulty, and we have here two angle sensors used in the system, as well as the ground speed sensor. Moreover, the user inputs and control level should be assured also. So this is, for example, a contract that's been marked with concern safety. So we can have also a contract that's been marked with security concern here. That is, the formal properties here have been marked with concern security, which means that the requirement that this contract addresses that we have specified here, it means that this requirement is a security requirement. So if we go here, this SV3, that would be this particular requirement. And this contract, for example, talks about that the loading arm request, automatic positioning request shall be authenticated. That is, each signal will come with an authentication flag, and if the flag is true, then the command will issue. If the flag is false, then it will disable the component. That means if we get an unauthenticated message, then we will disable the arm movement, so to say. And we can have different contracts for different things here. So each contract can be then described in different ways. Are there these assurance context statements? Are there certain evidence that we want to support this contract with? Once we have done that on the system side, once we have done that, what we would like to do is assure this in the OpenCert, the GSM-based assurance case. So what we can do here is automatically generate argument fragments. So I have already done that, and so we speed things up a bit. This would be the destination, and these are the different small diagrams generated for each of the components in the system. For example, for the whole component, and then for each of the subcomponents. So if we look at the top level, what we got here is, if we want to assure on this top level, then we have several contracts that we're assuring, and since these are mapped with different concerns, we have simply here divided things based on these concerns in the naming convention of these contracts. So this is the current implementation. What we could do in the future, if we decide to have separate modules, then these could be generated in different diagrams, different concern aspects. But for the moment, they are separated by the naming convention of the claims. So here we can see, for example, that we are showing this safety contract that relates to a safety requirement, which we can read here, for example, which is this particular first safety requirement, and this is the explanation of the contract, and then we are referring to the different aspects that support this contract, and we also point to the subcontracts or the contracts that this one depends on. And these are away goals that are located in other modules, in other diagrams. So for example, if we go to one of these, if you know this is the subcomponent, and this is one of the contracts that's referred to in that case. But the same thing we do for security. So this would be one security contract with all the different sub-goals, assuring its confidence. And this would be a contract in another module that's referring to it, for example, here. So what we can see, if we go to the model here, so we can perform different validation of the contract. And let's see here. And what we get in the end is whether the contract is, for example, here, whether the contract is validated or not. The contract status tells us this. So, for example, this one is not validated and this one is validated. Or if we check these, so these are, for example, not validated. So how is this propagated here? Then in one case, we have the supporting statement if they are validated, but in some cases, we have this challenging statement if they are not validated, which means that this is something that needs to be further checked. And this would be essential current support for multi-concern assurance based on the component contracts from the system domain. And that would be all from my side.
Okay, do you have any questions? No? Okay, so the next one is Gabriel, okay, from CEA, transfer your presenting rights. Okay, now I unmute you, okay, so it's your time, Gabriel.
Can you hear me?
Yes. Perfect.
Okay. Can you see what I'm sharing?
Yes, perfect. So you can start.
Okay. Okay. So, well, in this presentation, I will try to explain how Papyrus for safety and security engineering is being used in order to address multi-concern analysis. In this presentation, I will address two levels. In the first level, I will explain the conceptual issues, the conceptual aspects of this work, and in the second level, I will address the implementation aspects of the work. So, as you may know, the Papyrus approach is based upon a design model of the system. So the design model of the system can be developed in different languages like SysML, UML, RobotML, or other domain-specific languages. So the objective of these languages is to close the gap between the notions that could be generic and the notions that are related to some specific domain or to the needs of the engineers to develop and analyze the system. So basically, once the design model is achieved, our approach consists in annotate this model, either with safety properties or with security properties. So the goal of these annotations is to complete the model by adding the safety or security aspects that are necessary to conduct those analyses. Roughly, just to recall what does it mean, the safety model view allows to add, for instance, notions like accidental causes and effects of accidental risk, and the security model is able to support annotations dealing with the security threats that can target the system model. So basically, what we have here in this slide is that in the end, our approach is meant to support on one side a safety analysis and on the other side a security analysis. We have to consider that these modules were developed independently, and right now the safety analysis is the more mature part of the tool. So I can tell that what we can see in this slide represents the methodology that we are able to support for the safety and the security parts. So basically, the complexity now is to find how these modules that were independently developed can be reused for co-engineering. It means to conduct safety and security analysis. And finally, just to take advantage of the analysis that could be made independently. So, but how it looks like. So first, after going ahead with my presentation, I would like to show you the interfaces. So here we have a very basic example. This is a toy example. It represents a landing gear system. So basically, we have a global block that represents our system and all the components of this system. So this is the block development, block definition view. So I will show how it looks like once you develop the internal block diagram. So here we have the functions representing this landing gear system. It consists basically of a switch, electric switch, that is connected to a redundant system consisting of a transformer and a battery. These power sources are connected next to a couple of pumps that are next connected to a couple of valves. And finally, there is the landing gear system. As you can see, this is just a redundant system, and the objective is to provide enough safety for the landing gear. So what we can do with this basic example is just to apply the functionalities that are already supported in the tool. For instance, here we can apply the safety annotation. In a first step, we have to apply here the FTA and FMEA annotation. And once this has been made, we can observe that the blocks are stereotyped with the right stereotypes necessary to conduct the FMEA and FTA or whatever is in the profiles that we have chosen to conduct our analysis. So a quick overview of this, for instance, in the quantitative part of the FTA, here we have the failure probability, marginal importance factor, critical importance factor, etc. So some of these values are should be provided by the user. The others are calculated automatically. Well, here I'm experiencing some problems to show the final functionality. The objective of this module is to settle the failure modes and then analyze the criticality of each block. So here I'm gonna apply. I'm gonna define, for instance, a failure mode for this component. What I have to do is to go here, apply safety annotation, and then apply failure model. Yeah. And here we can see that there is an internal failure. So the user can proceed to complete it according to the failure mode that the user is trying to model. So finally, once all this has been completed, we can identify which are the critical blocks. And to do so, what we have to do is just to click here, show final critical blocks. But unfortunately, this functionality is not working. I don't know why. I can show you how it looks like here. So the objective of this is to see the critical blocks. It looks like this. So afterwards, we can generate reports, we can generate tables that can be local according to each component, or global according to the whole system. So let me show how it looks like. So here, for instance, we have the global failure modes and effects table. This is the summary table, and this is the complete table, showing all the properties. As I mentioned, this is just an example to show the functionalities, that this is operational. And well, this is for the safety part. And now I'm gonna show you the security part. So for the security part, sorry. Can you see the screen? Is it visible?
Yes.
Yes. Okay. So what we have here in this view is the front end of Papyrus for security. There are 8 phases that are supported, as you can see here in the Model Explorer. It starts, for instance, with the configuration of the scales that will be used for the security analysis. Here we can define, for instance, the security criteria that will be used for the analysis. It means integrity, availability, confidentiality, etc. You can also define a severity scale. This severity scale is used for the evaluation of risk. We can add knowledge bases, for instance, including the types of consequences of the attacks. This is important. Here we define the likelihood scale that will be used to calculate or compute the risk, the types of threats, finally, risk scale that is used as well to identify the risks that are not acceptable. Finally, we can see here, for instance, the risk evaluation matrix that is based upon the severity and likelihood scales. So once we have this perimeter and sorry, it's gone. Okay, once this perimeter and scope analysis definition has been made, we can proceed to the other phases. The definition of the primary assets, for instance, the association of these primary assets to security requirements. We can go ahead with the definition of supporting assets, the association with their vulnerabilities, the existing security control measures. We can, for instance, here make the definition of what is called the the threat scenario, which is only the definition of the attack and the association of this attack to the entry point, which is also named the attack vector, etc. I want to show you this for this. Once the definition of these attack scenarios is finished, we can structure these attacks relying upon these logic gates and produce what is named the attack tree. So finally, you can here obtain the risk for the period events you have defined. There are two ways to compute this risk regarding or considering the security criteria, and the other way is based upon the threat scenarios. So I will show you, for instance, how it works. You can perform a modification of your analysis afterwards to make a calculation of the risk. You can click here, take these elements that have been created, put it in the table, and normally you will have the update of the risk calculation. So this is just an overview of the tools. And what I wanted to show is just a flavor of how it looks like. So now the question is, how can we make a reuse of these implementations, a reuse of these conceptual artifacts for a co-engineering analysis? So basically, we have already a safety process and a security process. Two methodologies. We have identified some of the links that we can settle between those processes, but at the very beginning was really complicated to go ahead because there are many discussions on that, and it's difficult to find a consensus. So our entry point to address this aspect was to consider the standards, and a lot of literature that has been published in order to address this subject. So here I'm showing the proposal we are following. In this slide, I'm showing, for instance, how the safety assessment process and the security risk assessment process are correlated. And in the middle, you can see the system development process. So these kind of proposals, these kind of approaches are being considered in order to make to define in a first level the conceptual links between processes, and in the second level to implement these artifacts. So here we have a refined view, for instance, of the links that we have found between the ISO 27005 and a security standard that makes the relationship between safety and the security process. We have several concepts here. We can see that we can settle some links between those concepts, and also to find the relationship with other standards that are typically used for the safety process. So by settling these links, we can also settle some relationships between concepts, and to identify, for instance, the links between security and safety parts. So how it looks like, or how we plan to implement this. So basically, we will plan to support a model based on components that can be refined in subcomponents or subsystems, and those components are linked by interfaces that provide communication or data transfer. So what we plan to do is, for instance, to identify how the entry points for an attack impact the safety of the system. So in the figure here, we can identify what is named the attack path. So this attack path starts in an entry point that targets a first asset, which is also considered as a victim. This attack is later propagated to a second victim by undermining a security measure that could be deployed in this victim, and the propagation goes ahead just to the target asset. This target asset is what we name the threat condition. The threat condition is the previous asset that is compromised before a failure is produced in the system. So here we find the link between an attack, for instance, and the propagation of a failure in the system. So just to summarize the aspects we have identified to conduct multi-concern analysis. So first, as I mentioned, we have several standards that are considered for the conceptual definition of notions and the establishment and the settlement of links between those notions. Based upon these standards and other literature, we are identifying commonalities. Here the challenge is that there are semantical differences between syntactically similar concepts. For instance, the notion of period even. We have found that in several cases the notion of period even refers to different notions. We have also identified some particularities. For instance, the fact that the security criteria, namely integrity, confidentiality, authenticity, etc., don't have counterparts on the safety domain. So those are particularities that we have to consider and to support independently without trying to make a mapping to a safety counterpart. Equivalently, we have the safety notions that are particular to the safety domain, and we are not trying anymore to make a counterpart on security. These concepts include but are not limited to the accidental failure, failure rate, failure propagation, etc. Another aspect that is very important in our analysis is the evaluation metrics. We know that there are statistical and probability measures that have been applied. However, the nature of the safety events is not exactly the same to the security events, mainly because the safety events are based upon the physical nature of components, the exposition to operational conditions, and the security events are mostly based on motivation gains and rationales of human beings. So these rationales of human beings sometimes should be taken into account, for instance, to calculate the difficulty of an attack. When we are prompted to compute the difficulty of an attack, for instance, we have to consider aspects like the knowledge of the attacker, the intelligence, the skills, the resources, etc., which is far more complicated to just the propagation of a failure of a simple component. We have also identified that it's necessary to consider the integration of techniques. This is an aspect that has been already addressed in several papers in the literature, but we consider that we have other challenges that have not been clearly identified nor addressed. For instance, the fact that there are different abstraction levels in the models that we could try to link. For instance, if we independently develop a safety model, independently a security model, the abstraction levels might be different. Also, if we plan to integrate knowledge bases of attacks, vulnerability, attack scenarios, or plan to reuse which have been already defined, there is a complexity there considering the different abstraction levels. Finally, what we call the safety security domains border, we have identified that in general there is a sequencing in the application of those analyses. It means that first we usually find that there is a safety analysis which is conducted, and afterwards a security one, or conversely, a security and then a safety one. So there is, according to our knowledge, we don't have many cases in which a safety and security analysis is conducted in parallel at the same time. So considering these facts, considering these observations, we think that it's important to exploit the logical border that can be identified between the safety and the security spaces. And that's all. If you have questions.
No questions? Okay, thank you then, Gabriel.
Yep.
So let's move to the next slot, which is via Safety Architect by Mark Sango. Here I transfer you presenting rights. Yes. Okay. Mark?
Yes, you hear me?
Yes, yes. Perfect.
Okay. Okay. You see my, can you see my screen?
It's loading right now. Still empty.
Okay.
No, I can see it. It's still, it says it's like loading. something like that. It is empty right now. Now, perfect.
Okay. Thank you for attending this session. I will present safety and security co-analysis with safety architect. And when I talk about safety and security co-analysis, I don't speak about co-engineering. For co-analysis, I mean how we can review security artifacts to do a co-analysis in safety architect. So safety architect is Alphotech commercial tool, initially dedicated to support classical safety analysis method like failure mode analysis or fault tree analysis. And for the presentation, I will present the different feature of the tool. For example, there are 6 main features in the tool. You can import a model from different modeling tools like Papyrus, Capella, or IBM Rhapsody. And thanks to the series modeler, you can also model in the tool. And what is interesting in this presentation is the local analysis of the different elements of your model. So I will take a small time here to see how we can do safety and security co-analysis in different models. And then from this analysis, you can generate your propagation tree, and you can do some report like FMEA table, and you can also export the fault tree generated in Safety Architect to other fault tree tools. So let's go directly in the tool to see the demo. Can you see my screen, the Safety Architect tool? Hello?
I cannot see the screen.
You see?
Nope.
Not yet.
Now it's visible.
Okay, do you see Safety Architect tool? 3.0?
Yes.
Yeah, okay. As I say, in the tool, you can model directly in the tool, or you can import model from different modeling tool. For example, here I will import a basic model. For example, you can import Magic Do, Papyrus, Rhapsody, IBM System Architect, or Safety Architect model, of course. For example, here I will import a small example, a fire detector example. Quickly. Okay. So the tool import. The tool, when you create your model in Safety Architect, it is an Eclipse-based tool. You have 3 files. You have the .ird, which represents the graphical representation of your model, and your .sar, which is the different element of your model. And you are also the .fear event, where you can create your fear event. For example, if you identify some fear event in your primary hazard analysis, you can define this fear event here. For example, for the example, I define, for example, the fear event fire for the fire detector example. Okay, and in this context, we have to do some analysis to see how we can see the safety and security artifacts which can impact this failure event. So let's open an example. In safety architect, everything is a viewpoint, so the tool is based on the concept of viewpoint according to software and system architect standard. So the first viewpoint is the system modeling viewpoint. And in this viewpoint, you have, it is a gray box. You have the system, an input port, and the output port. And for example, for this example, the fire detector example, you have, for example, the data which can be the smoke of the fire, and you can have a parameter, the threshold parameter. According to this threshold parameter, the system can trigger a sprinkler or an alarm. Okay, and this is the high level of the system. And the next level is the system architecture viewpoint, where you describe the exchange between the system elements. For example, here everything is typed in safety architect. In the green, you have a function. So let's make some. In the green, you have the function of your system. For example, here you have the data acquisition function and the data processing function. And you can allocate your function in logical component. Here it is a software component. And you can also allocate your function or logical component to physical component. Here, for example, the hardware component processor. So this is a basic example to show how you can do safety and security co-analysis. So to do that, you have to select your viewpoint. For example, here you can select the safety and security viewpoint to do the analysis. For example, here I select the architecture, safety, and security viewpoint. And let's consider now the safety viewpoint of the data processing example. For example, here you can create safety and security viewpoint for the different elements. I already done this analysis, so I will open first the safety viewpoint of the data processing function. For example, in this function, we have different elements. When you open your safety viewpoint, the input and the output port is annotated with the failure mode. For example, here you can add a predefined failure mode, for example, absent, intempestive, erroneous, and you can add also specific failure mode to define your specific failure mode. For example, here I can name this specific loss of the sprinkler. Okay, and now you can begin the analysis of your element, here the function. And to do the analysis, the first, I can hide, for example, here. First, I say that to have the erroneous of this output, you have to have the erroneous of the input, the data, or the erroneous of the parameter. And this failure mode, you can associate also the cause of your failure or the failure detection. For example, here I say, for example, the verification of data. You can also consider the allocation relation. For example, here I say that if the component on which the function is allocated is failure, I can have the failure of this function. And the next thing important to annotate is the notion of barrier, and this concept is used to mitigate the propagation of failure in the element. For example, here I had a barrier named a watchdog barrier, and I say that to have the propagation of the failure, you have to have the failure of this barrier. So you can add also a failure mode in this barrier to say, for example, the cause of this failure mode can be the implementation error. So here it is the safety viewpoint in this function, and you can have also you can have also the safety viewpoint of software or hardware component. For example, here I show you the safety viewpoint of this component. For example, I say here, if the component, the hardware component is erroneous, my software component is also erroneous. I can do the same analysis in the hardware component. For example, here in the hardware component, you can have the internal failure of your component, and you can define the probability of failure of this component. For example, you have a predefined probability function. You can use it then and define your probability of failure of this hardware component. This is the safety viewpoint, for example, of the element. Let's consider now the security viewpoint of the element. But in the security viewpoint, I will consider, for example, here the data acquisition, which is allocated in the sensor. And this function is allocated in the sensor, and in this example, we can consider that the sensor are more vulnerability than other elements of the system. So for example, here I open the security viewpoint of this element. And in the security viewpoint, you have different elements where the artifact of security. For example, here I define the vulnerability mode of the input. I say that from, for example, vulnerability analysis, which can be done in another tool. For example, we have another tool named Cyber Architect. In Cyber Architect, you can do your security analysis. So you can reuse this security artifact in Safety Architect to say, for example, here I had a vulnerability mode, and this vulnerability mode can be exploited if there are an assertion, for example, here, if an attacker can manipulate this vulnerability remotely. Okay, and I say also I can add also an operation in my allocation relation to say that in the context of vulnerability and assertion, an attacker can take a control of the sensor to run the remote exploitation attack. All right. So I can go in the sensor now to see how I can do the security analysis. And in this, when you open the sensor, you have already the operation mode and in the allocation relation and the output of this sensor. And so the attacker can take this mode to do an attack. For example, can run the remote exploitation attack in the sensor, or it can modify the kernel of the BIOS in the context of the Okay. I open in the context of the vulnerability and the assertion of the element. So you see, when I come here, I see, for example, here I have I can do also the safety analysis of my sensor. This is different. In the safety analysis, I see that the sensor can have the internal failure, and this internal failure can, in this internal failure, you can lose the function, or you can have the failure of the bus. So now I do the analysis of this basic example. So you have the safety and the security viewpoint of the element. So now you can generate the propagation of this failure or this security artifact to see how we can have the failure event. So to do that in safety architect, you can just go in global analysis, run propagation, and in the propagation you can select your viewpoint. For example, here I can select to see the propagation of my failure in the safety viewpoint. So I can just generate the propagation for this failure. For example, here I generate the fault tree for the safety viewpoint. For example, here we see, for example, the propagation tree in the safety viewpoint. I can also generate the propagation in the safety now, which is interesting for the safety and the security viewpoint. So I will generate the propagation of the two artifacts according to the analysis of the safety and the security co-analysis. So I can do next. I will generate the propagation. So for example, here, this is the propagation of safety and security. And in the propagation, we can see, for example, the security artifact. You have the attacker. We can take the control of the sensor to run the remote exploitation of the data. So, so we can see in this, for example, this tree is different from the safety full tree. And we can see this an example. You can also export this propagation tree to see the graphical representation in dedicated tool. For example, I will export this full tree to the OpenPSA format. It is an open standard for full tree representation. So I will generate this in. I'll take the propagation tree for safety and security. I will put it in my desktop. Next, okay. And if and in App Analyst, I can open the graphical representation of this propagation tree. So we see, for example, here the graphical representation of the propagation tree with the probability of failure of the different elements, and you have also the security artifact.
Mark, sorry
Yeah.
for interrupting you. See, the screen is gray. Somehow you're putting one application on top of the desktop. Okay, perfect. Thank you.
Okay. It is clear now?
Yes. You can continue. Sorry.
Now I present, for example, here the graphical representation of safety and security propagation. For example, here we see, for example, the security artifact, for example, the vulnerability of the input, and you also see, for example, the safety artifact, for example, here the internal failure of the processor with the probability of failure of this processor. Okay, right. And what I can also present you, you can also generate the FMA table. For example, to do that, you can just go in reports and report. I say, for example, I can generate the safety and security report. I can also generate the FMICA report or a general report. Let's take FMICA report, and I will take, for example, the propagation of safety and security, and I will select some elements to report, for example, here. Do you see my screen? I change.
Yes, yes. Perfect.
Yes, okay. Now we see, for example, the FMK report from the analysis of the model. For example, here we have the threat of the fire detector, and you have also the safety artifact, for example, the erroneous of this data. So you have an item, the function, the failure mode, failure cause, and you can also you have the failure detection and the compensation provision. So I think I show you all the methodology of the tool. So to resume, in safety architect, you can import model. You can do also modeling in the tool, thanks to Series Modeler. You can do local analysis of your element. In local analysis, it is you can do the safety and security analysis. And security analysis, you reuse a security artifact from another tool. And from this local analysis, you can generate your propagation, and you can do the report of this analysis, and you can also export the artifact generated in Safety Architect to a dedicated tool, as I show you in the example. It is all for me. If you do you have a question?
Okay, I think there are no questions. Okay, so thank you, Mark.
Yeah.
Okay, so let's move to the last slot, which is by Zulkarnain of MDH. So thank you. I move the presentation rights to him. Okay.
Hi, can you hear me?
Yes, perfect. We can see you too. Okay.
Yep. So, my name is Zulkarnain Haider, and I'm from Maladalan University. And during this presentation, I am going to talk about system dependability co-analysis via Concerto flaw. The agenda for today's presentation is as follows. I will first provide an overview of Concerto flaw approach. Then I will talk about the system dependability co-analysis via Concerto flaw. I will explain attitude control system as a use case scenario for the methodology, And in that, I will describe and demonstrate the system definition. And then I will describe and demonstrate the dependability modeling and analysis. And finally, I will talk about the interpretation of the analysis results for multi-concern. So Concerto flaw is a failure logic analysis tool which qualitatively evaluate a component-based system given the failure behavior of individual components. The AMASS platform includes the Concerto flaw plugin via inclusion of chess toolset, and it enables to decorate components with dependability related information and then execute the failure logic analysis. And in the end, after the execution of failure logic analysis, it back propagates the analysis results on the original model. So what is the behavior of a component is in the presence of failure is specified using failure propagation transform calculus. What is the behavior of a component? That could be of four types, and that could be specified using FPTC rules. The first could be a component could behave as a sink. What this means is that if a failure is coming on the input port of the component, the component stops that failure and does not generate or propagate the failure on the output port of this component. The second behavior could be the source, that the component does not receive any failure on the input ports, but it still generates a failure on the output ports. That means the component itself is a source of failure. The component could transform a failure. What does that mean is it receives a failure on the input port and it changes the type of that failure on the output port. And the propagate behavior simply means that the component receives a failure on its input port and it simply propagates it as it is on the output port. And we have three main failure types which are specialized, which have two specialized scenarios for each. The first one is value, which could be of coarse or subtle type. And then we have a timing failure, which could be early or late. And then we have a provision, which could be omission or commission. So here I have a flowchart which defines the methodology of system dependability co-analysis via Concerto flaw. So we start with the system definition. What does that mean? That means that we have a functional model of the system. Either we define it or we start with a functional model of the system. And then we perform dependability modeling and analysis, which refers to Concerto flaw tool or failure logic analysis in this context. And then we interpret the results of failure logic analysis for all of concerns of our interest, which in this case are reliability, safety, and security. And then finally, we have a trade-off between these different attributes, and based on that, we reason whether the system is acceptably dependable and do we need refactoring or should we continue. What does this approach provides, or the purpose of this approach is that we get a qualitative evaluation of system dependability, that we could argue that is the system acceptably safe, secure, and reliable, or etc. if we are interested in other concerns. And then also at the same time we get support for design decisions so that we could introduce safety, security, and reliability measures accordingly. Or we, as a system designer, we could evaluate the trade-off and redesign if needed. So I will talk about all of these steps in detail one by one, that how we do each of this stage, and then also I will demonstrate it. But first I will talk about the use case scenario for which we considered as a system in this particular training. That is attitude control system, which refers to case study 11, which overall targets attitude and orbit control system of a satellite system. But in this specific use case, we only considered attitude control system, and that too in sun pointing mode. In sun pointing mode, attitude control system is required to control the orientation of the satellite relative to the sun. So here I have a block diagram of that simple attitude control system. I have an attitude control system block which acquires the estimated attitude of the satellite, which has been determined by the sensors. In this case, it is a sun sensor. And what it does, it calculates the difference between the estimated attitude and the targeted attitude. And based on that difference, it generates the control torques, and that has been transferred to attitude actuators to be applied on the body of the satellite. This sun pointing mode of attitude control system is basically inspired or required by the mission of the satellite. For example, in this case, the requirement is that the satellite should point to the sun to, for example, power up its system, or maybe in a space exploration system, it should point towards the sun to study the sun phenomena or something. This system is which we have been defining as an attitude control system is composed of 4 components in our implementation. The first component is a PD controller, and the second component we call it steer controller. The third component we call it feed forward controller. These all 3 components are implementing the controller with different strategies, and it computes the control torque to be applied on the satellite body. But we have another component which is torque selector, which takes all of these torques and decides which torque should be sent to attitude actuators to be applied on the satellite body. And that decision has been made based on the current strategy which is required in that scenario. These attitude control systems are required to be developed according to the European Corporation for Space Standardization. So ECSS standards for space product assurance have 2 dedicated documents for dependability and safety. The first one is ECSS Q30 and the second one ECSS Q40. And both of the dependability document mainly concerns or is focused on the reliability of the system, and then the second document is explicitly targeting safety. So yeah. Next, I start with the system definition, which I have given the flow for the methodology. So what does system definition means is to acquire a component-based architectural model of the system. In our case, we are using chess modeling language, which is is implemented as a profile of UML, SysML, and Marte modeling languages. In order to define a component-based system using chess modeling language, we first define the components and then the component implementations and their interfaces. And once we have all the components and their interfaces, what we do is provide a functional or assemble those components to compose the system, or in other words, we create a functional model of the system. I will give a quick demo of how this is done in a chess tool, which is incorporated in the AMASS. So we start with creating a new project of chess type, and I have already created an AOCS project which I want to create again. In AOCS project, we have an ACS model, and this is the welcome screen when we create it first. And if we go to Model Explorer of this Model Explorer, we have the chess model. And first we, as I described in the slide, that first we define the components, component implementations, and interfaces. So we go to component view, and inside component view, we create a new diagram of type class diagram where we define all of our components. In this case, I have this AOCS class diagram, which is going to open now. So in here, we could use this palette and define all of our component and their interactions and then their implementation. In our case, we have, as I described earlier, that we have 4 components: one PD controller, steer controller, feed forward controller, and then torque selector component. So I have modeled all of these components and then their interfaces and then their implementations. The second step is to assemble those components and compose a system. For this purpose, in this scenario, I have used an ACS composite component, which is composed of all those components and is being done in internal block diagram. So here I have the PD controller and then steer controller and feed forward controller, which are all of these components are connected to torque selector component, and then on the and they have input ports. The ACS composite component, which refers to the system, has the input ports which are connected to the sensor interface, and then here to the actuator interface. So we go back to the slide. So once we have an assembled system, we do dependability modeling and analysis. And in order to do the dependability modeling, we first have to decorate all of these individual components with dependability related information. And that means that for each of the component, we have to define that what should be the behavior of this component based on the failure it receives on its input port, and what should it emit on the output port of this component. And these rules could be specified using a specific language where we have the input port name and then the type of failure, and the output port name and the type of failure. Once we define the behavior for each of the component, we define the failures on the input ports of the systems, which are coming at the on the input port of the system. And then we define the analysis context, and finally we execute the analysis. We go back to the tool. I could demonstrate each of this step individually. So we start with defining the failure behavior for each of the component. And first we have PD. For example, we could start with feed forward controller. And if we go to the diagram, and here in the properties view, we have this test tab, and from here we could go to this FLA expression editor, and there we could write the rules for all of this, the behavior of this component. For example, the first rule here is describing that on the input port of this component, which is called gyro distributed torques, a value subtle type of failure could generate no failure on the feed forward torque. That means for this specific failure, it is syncing that failure. And then we have another rule which is defining that in case we have value course failure on this port, this could result in a value course on the output port of the component, that is feed forward torque. That means it's propagating that specific or failure. And after defining this, we define all of other components behavior as well in the similar fashion for PD controller, steer controller, and torque selector. Once we are done with defining those failure behaviors, we go back to our system and we decorate the system's input port with the failures. In this case, here we have three input ports of the system. One is sun estimated vector, which is the sensor data of sun. And then we have angular velocity and the gyro distributed torques. And we have defined so we have defined the inputs, the failures on the input of all of these three input ports. In our case, we are expecting that all of these input ports have value subtle and value coarse type of errors, failures. And once we are done defining the failures on the input port, we define as we go and recall from the slide, we define the analysis context. That is done in the model analysis view. Inside dependability analysis view, we create a new class diagram. And then we create a failure propagation analysis stereotyped component, and then we assign the context to this. Yes, so we assign the context to. I have somewhere in the picture which I could show it later. So after assigning the context to this dependability analysis, failure propagation analysis stereotype component, we go to our system and then we execute the analysis or invoke the analysis. That could be done from this taskbar, from this. So we go to analysis, we go to dependability, and then we run failure logic analysis. And this generates the failure logic analysis results. So after invoking and executing the analysis, the next step is to analyze the to analyze the results of the analysis. And inside this, the first thing which the tool enables is the back propagation of the results to original model. And then at the same time, in addition to back propagation, the tool also produce a specification of the results represented in the FLA meta model, and that could be visualized as failure propagation paths. I would demonstrate these three steps in the tool as well. So if we go to our system component, we have, after executing the analysis, we have these comments have been generated, which are associated to the output port. If we drag one to the system, we could see that it is bound with and connected to the output port of the system, and it has we could select what sort of information we need to see. So we want to see that what have been the results on the control torque based on the rules we have defined. So we could just disable the extra information which we don't need. So on the execution of analysis, what we could see that based on the rules which we have defined for each of the component, we receive value coarse and value subtle type of failures on our control torque output port. In addition to this back propagation, it also generates the FLA analysis results in this folder and in FLA meta model that could be visualized as in a text editor to see all of the failure types and the rules, and then the back tracking. But the more effective way to visualize it is through Modisco model browser, and in there we could actually see all the information which is required or needed to interpret the results for different concerns. For example, in our case, the ACS composite component, which is representing the system, has 3 output ports, but we are interested in control torque port. And this, if we keep browsing, we see that we have 2 types of failures on this port. One is value coarse and one is value subtle. And if we get into more details of value coarse, we see that we have previous failures associated to it, which represents the failures which contributed to generate this failure. And we could actually backtrace to the causing failures till the beginning of the system, and so on. So yeah, I'll get back to the presentation. So once we have the failure propagation paths, what we could do is manually interpret these results for multi-concern. And for reliability concern, what we can do is to generate a fault tree analysis, so that the failure which we have on the output port of the system could be considered as a top event of the fault tree. In this case, for example, we have manually constructed a semi-fault tree, and then the top event could be interpreted as ACS attitude control system provides inaccurate torques. And then we, using the tool And this tree-like view, we could actually back trace to all of the previous failures and step by step generate the contributing failure events for the fault tree. In addition to this, we could also interpret those results for the safety concern by generating the fault tree for the safety concern where top event is a hazardous event. But in case of satellite systems, typically the satellite systems are do not have any human except for the spaces stations. So it's most of the time the top event is a system level failure event. And then for security concern, we could also use these failure propagation paths to construct attack tree and an attack tree where system level failure could be interpreted as an attack goal, and then all the contributing failures could be seen as a result of tampering or spoofing by an attacker. And once we have all the interpretations of all of the concerns, we could perform or evaluate the trade-offs, and the system designer could redesign if it is needed. Yes. Thank you, and that's all from my side. If you have any questions.
Okay, if you have any questions regarding this slot or any other you may have find out during the sessions, just let us know. No questions? Okay, so I think it's over. So thank you very much for attending these sessions. Please remember that this is the first session of WP4 training. There will be another second session tomorrow I think, or on Monday. I don't remember exactly. Please take into account these sessions just to attend. Okay? Thank you very much.
Thank you. Bye.
Bye-bye.
Bye.
Bye. Thank you.
Bye.